Let's solve some exercises on FT modules associated to matrices. So what we've seen is that if you're given a matrix A, so let's say A is an n by n matrix over some field F, then you have this gives rise to an FT module. In this FT module, the underlying additive abelian group is just f to the n, and given a polynomial a0 plus a1t plus a dt to the d, this acts on a vector v belonging to Fn by a0 plus a1 times the matrix A plus ad a to the power d. This whole thing is a matrix multiplied by v. And every FT module arises in this manner. So here's the first exercise. Find a matrix A. In this case it will be a 3 by 3 matrix over Q such that the associated A module, let's call this M subscript A, is isomorphic to Ft mod t cube minus 2t squared plus t minus 3. So there are many ways to solve this problem. What you have to do is you have to pick a basis for this module, and then the matrix will just be however t acts on with respect to that basis. So pick a basis. So E0 equals 1, E1 equals t, by which I mean the image of 1 in Ft mod t cube minus 2t squared plus t minus 3. E1 is the image of t in this module. E2 equals t squared. And then t cubed is 2t squared minus t plus 3, because t squared minus 2t plus t minus 3 is 0 in this module. So this is no longer independent of E0, E1 and E2. So E0, E1 and E2 form a basis of this module. And so let's figure out how t acts on this. So t E0, well, it's just t times 1, that is E1. T E1 is E2, and t E2 is t cubed, so it is 3 E0 minus E1 plus 2 E2. So therefore the matrix A has the form, the image of E0 is E1, so the second basis vector, the image of E1 is E2, the third basis vector, and the image of E2 is 3 E0 minus E1 plus 2 E2. Let's try another similar exercise. Write down a matrix A belong to M3. So this the size of the matrix is always the dimension of the module as a vector space over the field F. So we'll work with the field Q here. Actually in this maybe I can take any field F, it doesn't matter, such that MA is isomorphic to Ft mod t squared direct sum ft mod t. So again, to solve this we have to pick a basis. So I'll pick a basis e1 equals, so there are two summands here, so I'll take firstly the 1 from the first summand and 0 in the second summand, e2 to be t from the first summand, 0 from the second summand, and t squared in the first summand is 0, so I can stop here. That's two-dimensional, and this thing summand I'll just take 0 comma 1. Then let's figure out how t acts on these basis vectors. Then t e1 is e2, t e2, well, it's t squared, so that's 0, and t e3 is also 0. So the matrix A is just going to be 0 1 0 0 0 0 0 0 0. That's it. Exercise 2 3. Find A such that MA is isomorphic to FT mod t minus 3 whole cubed. I'll solve this in two different ways. First, I'll take basis E0 equals 1, E1 equals t minus 3, E2 equals t minus 3 squared. And then what I get is t times E0, well, it's t, but I need to expand in terms of this basis E0, E1, E2. So I can write this as t minus 3 plus 3, which is E1 plus 3E0. And TE1 is t into t minus 3, which is t minus 3 whole squared plus 3 into t minus 3, which is E2 plus 3E1, and TE2 is t into t minus 3 whole squared, which is t minus 3 whole cube plus 3 into t minus 3 whole squared, but t minus 3 whole cubed is 0 in this module, and so this is just E2, 3E2. So then we get that the matrix of A is so E0 goes to 3E0 plus E1, E1 goes to 3E1 plus E2, E2 goes to 3E2. This is a Jordan block with eigenvalue 3. Of course, we could have also done this the stupid way. We could have taken E0 equals 1, E1 equals t, E2 equals t squared, and using the fact that t minus 3 whole cubed is equal to t cubed minus 9t squared plus 27t minus 27, we could have written A is equal to 0 1 0 0 0 1 27 minus 27 9, which would also be a correct answer, but I like the first one better. Okay, now let's look at a fourth exercise where we have ft equals not ft, ma, find A such that ma is isomorphic to ft mod t minus a whole squared plus ft mod t minus a, where a is some element of f. So the way I'll solve this, I will take my basis E1 to be 1 comma 0, that is the one of the first summand, E2 to be t minus a comma 0, and then I'll take e3 to be 0 comma 1, and then I find that t times e1 is t minus a, which is t minus a plus a, which is e0, rather e1, a times e1 plus e2. This is all happening in the first component. Maybe I should put zeros here, but t e2 is equal to t into t minus a comma 0. Of course, I'm not writing that, which is t minus a squared plus a into t minus a, which is equal to a e2 plus e3. A e2 plus not e3 plus 0, because this part, well, it's 0 in the first component. And now when we work with TE3, we'll be working in the second component. TE3 is equal to t times t minus a, no, it's just t, which is t minus a plus a, but t minus a is 0 in the second component, and so we just get a e3. So the matrix here is a 1 0 0 a 0 0 0 a. So this is a matrix in a Jordan canonical form with two blocks, one of size 2 and one of size 1. Both blocks have eigenvalue a.